All right, so we are going to do problem 5.72a. So if we go through and read the problem, a thick oak wall, initially at 25 degrees Celsius, is suddenly exposed to combustion products of which T infinity equals 800 degrees Celsius and H equals 20 watts per meter squared Kelvin. Determine the time of exposure required for the surface to reach the ignition temperature of 400 degrees Celsius. So what we're going to do is we are going to start off with the givens. So first we have T initial equals 25 degrees Celsius. We have T infinity equals 800 degrees Celsius, and H equals 20 watts per meter squared Kelvin. We want to find T, the time, at 400 degrees Celsius, which for this problem we're going to call T at 0, T. So next, some assumptions. The first assumption is we're going to make is it's a semi-infinite solid. And we're also just going to assume 1D conduction. So that's kind of like setting up our problem. We do need to pull some properties. And this will be, we'll just assume at 300 Kelvin. We're just going to pull those for that temperature. We're going to say rho equals 545 kilograms per meter cubed. K equals 0.17 watts per meter Kelvin, and CP equals 2385 joules per kilogram Kelvin. And we're just going to calculate this now because we are going to need it later, but equals K over rho CP, which if you do calculations comes out to 1.31 times 10 to the negative 7th meter squared per second. Okay. So when we are using this, we are assuming that it is a semi-infinite solid with surface convection. So this, in your textbook, if you look, there's multiple cases. This is case 3, and we'll be using this chart right here. So basically, what we need to do is find this temperature kind of delta ratio as well as this. And then on this chart, then we will be able to find the value of which this equation equals, and then from there we'll be able to solve for T. So let's start with finding the delta. Zoom out a little bit. So for this, we have T of 0, T minus T initial all over T infinity minus T initial, which equals 400 minus 25 all over 800 minus 25. And when you do that calculations, it comes out to 0.48. And then for the other one, we have x over 2 alpha t to the 1/2, which equals, we don't even need to put in the alpha or the t because x is at 0. So we have 0 equals 2 over alpha t over 1/2, which equals 0. So then if we go back to this chart, you can see from this chart we'll be at 0. And then if you go up to 0.48, you'll find that we are around 0.75. So that's going to be like somewhere around here. So yeah, so then we'll be able to use this, we'll be able to use this equation here and then back solve for t. So again, from the figure, and again, you can find that figure in your textbook, h alpha t square root of that over k is about 0.75. Okay, so when you rearrange this all for t, you will get t equals 0.75k over h alpha to the 1/2 all squared. And what I did was I just booped the alpha on the inside of the parentheses just to make it a little bit easier when we're writing it out. That equals 0.75. Thermal conductivity we found before. Properties, watts per meter of Kelvin, all over h, which h was one of the givens that we had. That is 20 watts per meter squared Kelvin. And then 1.31 times 10 to the negative 7th second. And this is all to the 1/2. And then all of this is squared. And then when you do the math, you get t equals 310 seconds. And just kind of zooming out so you can see the full problem. So yeah, that is the answer for 5.72a.